the struggle of having teal right before fourth period.
Your brain just shuts off.
Okay.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot, what does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy, or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there, because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this pH.
So what did you say about metals?
They're going to transfer heat more readily.
So metals, basically you said metals can transfer heat more readily, right? But what does that make them? Conductors, right? So you saw on your web quest a little bit of information about conductors and insulators. So metals are conductors. So what would you say brick and wood would be?
Insulators.
More insulators. They might be slightly conductive because of just some of their properties, but they're more likely to be insulators. So do not conduct heat. Do not allow for heat transfer to occur.
ET simulation, so I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is...
So you just learned how a thermometer works. What happened? What do you say? Increases heat, does what to the molecules? Speeds them up, kinetic energy is increased. Okay? And what did they do? What did the molecules on the iron do to the probably like some sort of alcohol that's in the thermometer? It's no longer mercury, it's alcohol based. What does it do to them? Heats them up, speeds them up, and then they expand and they just look like they're rising. That's how a thermometer works. It's kind of cool.
We're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button, and now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually...
So he keeps saying surroundings. What is he referring to as the surroundings? The environment, you're right. And when he had the metal outside, he said the surroundings were just like the air around it. But when you put it in the water, what is the surroundings? The water, but the system is what? So basically the rule is heat energy is transferred between two things, system and surroundings. If water is the surroundings, what was the system? The iron, the metal, the thing we put in the water. So we're going to really start to use the word system and surroundings and at least identify which is which at first before we start a lot of these problems. This is an example of calorimetry where you have heat transfer between one object that's a hotter body and a colder body. And that's what we saw the energy transfer between the two.
Actually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. And remember the Maxwell-Boltzmann distribution shows us how that works. If we were to look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we...
So that graph, sorry, it's just kind of disappeared. This graph was on our reading from the Does Cold Exist? And I didn't talk about it then. I want to talk about it just briefly now. Basically, so the average is the peak. That peak on the hot graph versus the peak on the cold graph. The peak at the hot is farther to the right, which represents it's of higher energy. So the average is the peak. Therefore, that's average kinetic energy. And that's just not related to temperature. And that's why the one that shifted to the right side is actually hotter. So that's just we don't really need to know a whole lot, just the definition.
Ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance.
All right, before he goes into this, somebody tell me what you think heat capacity means, or what is just generically capacity mean? Something how it's the amount something can hold, right? Capacity is like, you know, this water bottle has a capacity of apparently 24 ounces, something like that. So, heat capacity would be referring to the amount of what it can hold? Heat, right? So, if I were to go to, what would be more enjoyable? To go to the ocean and swim in late October or late March?
October.
Why?
Because the heat is from the summer.
It'll still be hot in the summer, but it's October. Months later, no, you're right. The heat stays in it. So that means water has a really high heat capacity. It has a large amount of heat it can hold. You see what you just told me, though? You literally just told me the water is still heated because it can hold on to the heat better. So, but over the course of October, November, December, January, February, and then March, it's had a longer time to slowly lose that heat over that long period of time. So that's why it's probably going to be like pretty cold in May, even though it's starting to be spring. Hasn't had enough time to heat back up. So basically what you told me was that water changes its temperature very slowly. Its temperature very slowly because it holds onto its heat very, very well. But if you put some aluminum foil out in the sun, you feel it 10 minutes later, it's probably warm. It's probably pretty dang warm. And gold, if you just have some gold laying around, go put it out in the sun, it's probably going to feel pretty warm too. Just like if you put a cast iron skillet or any kind of metal object on a stove, it's going to heat up fast. And that's because of this low heat capacity. 0.126, 0.9, those are really, really low numbers. So that means that whenever you increase if you add heat to aluminum, it's going to take that heat, it's going to take those joules per gram, but it's going to increase its temperature really quick. So the K, or the Celsius for us, is going to increase quickly. This means it can hold up to 4 joules of energy before it would actually change a degree Celsius. This only holds like less than 1 joule of energy before it changes by 1 degree Celsius. So that's basically what specific heat capacity is, and we'll have like a little blurb about it again in a second.
So we use a term called specific heat capacity to measure that. And so right here you can imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy per gram, and then Kelvin, or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed, the amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum are heating up more readily than the water. Now the energy is going to be the same, it's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to...
Yeah, we totally learned that. All right, cool. So I'm going to jump forward to kind of get you moving for a second, and then we'll come back to talk a bit more about system and surroundings. So you guys have a colorful piece of paper. A lot of you use that gas ball like it was like gold. So I thought I was trying to help you again here. Sometimes it's going to have a visual that's a constant visual. Because when you start to memorize, like some of us are visual learners, we start to memorize, okay, that was on the first flap, that was Q equals N cap. That was on the second flap, that was Q equals mole times delta H. So you have this like visual trigger that makes you remember what you've already learned. Okay, so basically it is a 4 flat foldable. So I'll give you scissors in a second. Just take your long sheet of paper and fold it so you have like 2 doors. Okay, so this is going to be like active notes where you're writing down the formulas, the reason why you would actually use that formula, and you'll actually solve a problem with it. So just make it so you have 2 folds, and then draw a line in the middle so that you know where to cut it later. So I've already cut mine. You can see I've got 2 flaps and 2 flats. And on your the white paper you picked up, look for the instructions in the foldable and read those for a second while you're waiting on the rest of this. Foldables kind of seem cheesy sometimes, but they're helpful whenever you have one go-to piece of paper that you will use until you kind of get it by yourself. So whenever we start to label these, label it so you've got 4 quadrants. Label the first one, Q equals MC delta T. So that's the upper left one. Label this the one down below it, so the lower left, Q equals moles times delta H. My little perfectionist people, make sure you're writing this down too. The upper right one, negative Q of system equals positive Q of surroundings. That's this right here. I just don't have enough space to write it. You can write big. You'll have space on the inside for the notes, definitely. And then the last one is thermochemical BCE. So just put therm BCE. So that's basically all of thermochem right there. Thermochemistry is a very short unit for us, and so it's combined with another unit. So we will be done with thermochem by the middle of next week. And a lot of it you're actually somewhat familiar with because we talked about phase diagram, phase changes already. We just now have to kind of put them into mathematical application, and everything will be related to a lab. So we have 2 labs this unit, one with using Q equals MCAT and one with using Q of phase change. So we're going to refer to each of these today. So whenever we're going to say write down the description, that's what the first thing is. Like, you're going to write down why you would use this equation, and then give it a quick example of what each of the variables represent and the units that they regard to. And then if you can draw a picture representing what would the scenario look like, it'll be helpful to remember when you should use each equation. So I'm going to go to Q equals MCAT first, and I'll come back and I'll do the other ones. So here we go. Q equals MCAT. That's how I make the fold. That's how you fold it. You go like this. I know it's a struggle. There you go. Okay, so this information for 1 is what goes under flap 1. So that's a description of what Q equals MCAT or MC delta T would be used for. So I'll give you guys a second there. Just write down number 1 for a second. Okay. So whenever you use Q equals MCAT, it's because you're just simply measuring the heat content of the metal or of one substance. So if I put some aluminum foil out in the sun, and I calculated I had its initial temperature, and then I had the temperature after 5 minutes, I would have just established delta T. Delta T is T final minus T initial. And what are the units that you've seen already that delta T would be representing? And let me remind you, I would be measuring this with a thermometer. What is a thermometer measuring? Celsius. Okay, so this is going to be in degrees Celsius. In gases, we use Kelvin like it's nobody's business. In thermochem, we use Celsius 100% of the time. Okay, You'll see a couple instances where you see Kelvin, but we're going to go with Celsius. Okay. So the metal is going to be weighing 20 grams. Okay. So the aluminum foil I'll put out in the sun, let's say it weighs 20 grams. Well, that's mass. So mass is going to be measured in what unit? Grams, right. C is specific heat capacity. So why do you think it's labeled C? Capacity. It's talking about the capacity that the metal has to take in heat before it changes temperature. So specific heat capacity has 3 words, so it has 3 units. Ready? Joules per gram degree C. So it's got one of those big honking units like R had before. So joules per gram degree C. So joules per gram degree C. So what unit do you think Q is in? Joules. Okay? Heat. Q is heat, and heat is energy, and energy is represented by joules. So Q is heat, and that's going to be represented by joules. Okay, so in a problem like this, you're not really going to be transferring heat from a system to a surrounding. It's just literally calculating the heat of that object. So my example was putting a piece of aluminum foil out in the sun. If you want to write down an example, what would that mean? All right, so let's look at, actually, let's look at MCAT equals MCAT. Well, I'll come back to the other video. What's up? Yeah, T final minus T initial. TF minus TI. T final minus T initial. Okay, so let's go to this, the box, I think, one down. Nope, what have I just done? Okay, this one right here, number 2, is with Q system equals Q surrounding. So it's the one on the upper right. But you'll notice Q is here again, right? Q equals Q. Well, before we write this down, what does Q equal?
Heat.
Heat. What does it equal in terms of a formula? A formula. MCAT. Okay, so if I say Q equals Q, technically I'm saying MCAT equals MCAT. So do you see what I've done here? I just rewrote it in expanded form. So I'll let you write down a little bit of that under the description and then the formulas. Mm-hmm. I'll highlight or move that. Should be all right. Can I start explaining? Give you one more second. Okay. Okay, so whenever whenever one object is hotter than the other object, will heat be transferred? Yes or no?
Yes.
Yes. And when will they stop transferring heat?
Thermal equilibrium.
When they're at the same temperature, meaning thermal equilibrium, okay? So this is when you have 2 objects coming together and somebody has more energy than the other, and so they transition until they both have the same amount of energy. That whole thought process is called calorimetry. So calorimetry, most of the time in our scenarios, will have a metal, and I'm going to put a hot metal, because usually we heat up a metal we can heat it up quickly. That's what we choose to heat that one up versus water. So we'll have a metal that's coming into contact with water. Okay, and so those are that's like our system and our surroundings. That's our 2 substances coming together. And the hot metal is going to come into contact with the cooler water or the cold water. It's going to energy transfer until they're equal. And so what we assume is happening is that 100% of that energy is transferred without losing any extra energy as heat. Well, we know that's probably not exactly true, because like our bodies right now are releasing heat to the atmosphere. Everything loses heat. Everything loses energy as heat. But we're hoping that all that heat can be captured. And that's what we do in an experiment. So this is on the premise of the law of conservation of energy. Well, what does that kind of sound like? Of mass, right? Well, mass has energy because it inherently has bonds and all these things that can be releasing energy or taking in energy. So we assume that's 100% transferred. So the heat or Q lost or gained by the system is equal to the heat lost or gained by the surroundings. So if the metal is hot and it comes in contact with cold water, is the metal going to lose energy or gain energy? Lose. And how would you represent a loss of energy? As a positive sign or a negative sign? Negative. So I'm just going to write it here for you guys. I put a negative sign in front of the system with my scenario given here. So then who would be gaining the energy?
Water.
Water. So it would have a positive sign on the surroundings, right? So basically, one of them is going to have a positive sign and one's going to have a negative sign based on the flow of energy. And so then usually we substitute MCAT in for Q, and we'll stop for one of these. So in a problem like this, I would give you two masses, like mass of metal, mass of water. I would give you the C of the metal, the C of the water, and the temperature change of one, but maybe not the other. So basically there are 6 variables here, yes? I would give you 5, you would solve for the 6. Algebra, okay? So we'll be using that one in a second. So while we're still on system and surroundings, I'm going to let you guys watch the video on system and surroundings, so I'll give you a quick break from this, and then we'll do a last one and calculating. So this is the same guy. He's usually pretty concise, and some of the stuff you've seen before, so tell me what's new here.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat, and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction. So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat, it's taking it from the surrounding, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place, so in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reactions. Now in the lab, we can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed.
Okay, so how much of this is new so far? Not much. Do you remember a little bit of endothermic and exothermic? That was like the tail end of stoichiometry. We did delta H's. Delta H was called enthalpy. And then we did delta S's, and that was called entropy. But this is all about enthalpy, the thermal part of it, okay? So if you don't know that, exothermic reactions release heat. Think of it as exo is exiting, heat is released. Would that have a delta H of positive or negative? So, okay, talk to yourself here. It's exiting, it's going away, it's being subtracted, it's going bye-bye. Whatever you guys say. Negative. It has a negative, from the system's perspective, it is losing stuff. And so it's losing heat, it's negative. From the system's perspective, it's either, it might be getting colder. Well, I mean, taking in energy. I'll tell you why it's cold in a second. But it's taking in energy that's being added to the system. So that's a positive delta H. So if you don't know that, write it on the back of your foldable for yourself, okay? And then secondly, I cannot measure heat very well. What is the unit of heat again? Joules. I got a scale that measures mass. I have a thermometer that measures in degrees Celsius. And I have some other equipment that measures other stuff. I have nothing that measures joules. So we have to depend upon the thermometer to do it for us because we know the relationship between joules and temperature change now. So, all right. There's going to be some diagrams. You're going to want to draw those when we get here. And you'll
now, a really neat way to observe this is to use a model, is to use a energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy than the products. Now, where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products. And so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now, this is a really intense reaction, and it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at the energy diagram of this over time as it progresses, we'd find that these reactants, the iron oxide and the aluminum, have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so,
okay, so you've seen this before. You were drawing this way back, like a month ago. If you don't, draw it in the back of your foldable, okay? So this is an enthalpy diagram where he told us that the reactants have a higher amount of energy in their bonds, and the products have a lower amount of energy in their bonds. So there's an energy difference between the reactants and the products. Well, how many blocks is that energy difference according to the grid? 2, right? Because it's just the difference between where the reactant line is and where the product line is. It's just difficult to see because you've got this activation energy represented here. So this right here, energy difference, is called delta H. That's our enthalpy or our heat of reaction or whatever we're going to call it, heat of fusion, whatever is happening here. So in that particular one, is that delta H positive or negative? Because it's exothermic and it's releasing energy. So the reactants release that amount of energy to form products. So then what would the endothermic curve look like? Draw it in the air for me. Okay, so we started here, we had hump, and then we did there. Okay, cool. So I'm going to show that one here. I just have to erase this a little bit because it's going to show up on screen. Okay, so this is review, but I just want to make sure you understood there was a difference between system and surroundings. And then the endothermic one looks like this. So this is what a cold pack would do. A cold pack, like an ice pack, whenever you have reactants, they require energy to react. So you put a little bit of energy in there, and that's usually something that's on the inside the cold pack. You have to break or something, and it releases a chemical and it reacts. So that's going to take energy in, and then the products are going to be at the end at a higher energy level. But why is it cold?
Protects the heat.
From where?
From your skin.
From your skin. You are the surroundings in this case, right? The reaction is the system, so the cold pack is the system. So to you it feels cold, but as it's using up the energy, that's why it's using up the energy from you, that's why it feels cold. So those are endothermic reaction there. So exothermic reactions, does the temperature increase or decrease? Exothermic reactions, the surroundings, so if you're holding an exothermic reaction, would it feel hotter or colder? It would feel hotter because it's putting heat out to you and you're feeling that. From an endothermic perspective, if you had something in your hand that had an endothermic reaction happening, it would feel colder to you. So you have to like talk to yourself about who's the system, who's the surroundings, and what's actually changing. All right, so let's go back here. I'm actually going to go ahead and do 2 problems before I move on to our other one. Okay, so let's look here first. And this is on the lecture sheet that I gave you guys. It's 1 through 4, reading number 1. Ooh, I'll put the light here. So before we finish up our foldable, let's go ahead and do number 1. And you'll see I actually printed PS17 for you. You see that? Yay! Okay, so look at number 1 on the lecture notes. Everybody's looking there for me. You're going to have something to write on, notes preferably. Okay, so I want to go through like we did in gas laws. I want you to tell me which equation we're using from what we just learned based off the data given in the question. All right, so what do I know on this question so far? Let me start anywhere. So what variable is that? M, right? So we know M. M is 1.55 grams, according to the stainless steel weighing 1.55 grams. All right, what else do we have? What is that? What variable?
Q.
Q, you know, just the other way?
Yeah.
Okay, Q. And so basically, if you don't know heat is represented as joules, then that's difficult to know. But heat is joules, 141 joules. Okay, what else do we know? T, we know delta T, is that what you mean?
Yeah.
Okay, because it says the temperature. It doesn't say it's final. It specifically says the temperature is increased by that amount. So it's telling you the change. Do you see?
Yeah.
You just have to read a little closer. But it doesn't give you initial either, so I'm just going to go, that's delta T. That is the temperature change, 178 degrees Celsius, which we do not have to change the Kelvin. Yay. Okay, what is the specific heat capacity of stainless steel? What are we looking for? Looking for C. Okay, you should be able to deduce which equation we should use. Q equals MCAT, right? Okay, so these are not, and they're not that different from gas laws because you have a standard couple of laws or rules, equations. You look for data, you figure out which one applies, and you roll with it. It's not too different. It's just word problems and picking out the information. So Q equals MCAT. So I hear calculators coming out, yay. I heard one. There should be more than one. Okay. So M, and I'm gonna put my units in there and everything, guys. C. Oh, you know, before we start plugging, can we isolate C? What do I need to do?
Yeah.
C equals.
Divided by MC.
So MAP. Okay. Q divided by MAP gives us C. All right, cool. So now I can put in 141 joules for my Q. My mass is 1.55 grams, and my delta T is 178 degrees Celsius. Drum roll, tell me what your C is.
1.192.
You multiply, you got to put the parentheses on the denominator because you actually ended up multiplying by 178. Point what? 0.511 is what I got. What do you have some different ones. Your calculator doesn't know what's going on. These darn calculators, not reading our minds. So, 0.1 or 0.511. What are the units though?
Gram.
That's one of them. Joules per grams degrees Celsius. Do you notice that none of those units canceled out? So guess what? They were all still there. Okay, and that makes sense because the definition of specific heat capacity is the energy it takes to raise 1 gram of that substance by 1 degree Celsius. So all those terms are going to be represented as units. All right, so this is the specific heat of the metal. There we go. That's what you do Q MCAT. Hard?
No.
No. Okay, so let's do one that is a little bit more difficult, which is MCAT equals MCAT, because just we have more variables involved. That's number 1 on the next part. Oh, sorry, let me, before I go much further, does this make sense for the specific heat capacity of a metal? Why? It's really low, so what happens to its temperature as you add heat?
Oh, it heats fast.
Really fast, right? Because it's going to only hold 0.5 joules before it increases in temperature, and then 0.5 more joules, and then it increases in temperature. It just heats up very quickly. So this makes sense for a metal. I have a weird smiling face there. Okay.
So it's always going to be a J over.
Yep, J, joules over gram degree C. Good. Okay, so this one's a little bit more difficult. This is calorimetry, where we have to transfer heat between 2 different substances. So I like to make a table to represent my data table because it gets a little messy in the end. So what 2 substances are involved here? Metal and water. Okay, so here's my data table, M, C, delta, T. Just to kind of get my life organized, that's what I do at first. Do this from the first one for me, and then from there you can adjust to whatever helps you best. Okay, so let's go baby steps. What's the first thing I write down? Hold on, what's my question? What is the specific heat of the metal, right? So what am I looking for? C of metal. So this is metal, by the way. Okay. So that's my question mark. Okay. Now what do I know? 50 grams of metal, so that goes in the M of the metal box. And, well, how much is 100 milliliters? In grams. Remember, mass is in grams. 100 grams. And that is only true for water. Water has this great density of 1 gram per 1 milliliter. So 100 milliliters is 100 grams as well. So that's going to go in the mass of water. Okay? Is what? Right, so this is the temperature change of water, but just to verify, T delta T would be T final minus T initial, and that is 36 minus 34, because this is the final and this is the initial. So that would be 2 degrees Celsius. And that's for water. So basically, you just need to make sure your data that you're talking about for water stays with the water stuff and metal stays with the metal stuff. Okay, the initial temperature of the metal was 95. The final temperature of the water and the metal was 36. So how do I figure out delta T for metal? 36 minus 95. Good, because this is the initial for water, or metal, and everybody ends at thermal equilibrium at the same temperature at 36. So what is that? Negative 59 degrees C. Hola. Oh, stuff. I'll give you. Yeah, I haven't signed that yet. I'll give it to you. Can you come back at the end of class?
No, the nurse like got mad at me.
I'm in the middle of this great problem.
That's what I told her. She's like, no, I get it.
Okay, so you guys finish this problem. Finish filling out the data table. I refuse.
I was like, can I just bring it later? And she's like, no, it's free now. I'm like, my fourth period teacher's not even here.
I'll force your signature. Fine. All right, what else do you know here? Down here is negative 59. And then what's the C for water? 4.18. Did we write that down earlier? It was on the web quiz. What? All right. So I'm going to scroll back for you just to verify. Well, I'll go back in a second. You need to know the specific heat capacity of water of 4.18 joules per gram degree C. Sometimes I'll put like 4.184, 4.186. It varies a bit depending on what tables and data you're looking at, but 4.18 joules per gram degree C is good. Okay. So what of using this knowledge, what equation are we going to have to use? Right, so Q system equals Q surroundings, which is actually MCAT equals MCAT, right? But we need to figure out who's the system and who's the surroundings. Take a stab at it. Right, so the water is the surroundings and the metal is the system. Who's losing energy? The metal, because it's dropping in temperature. It's a negative 59 degrees Celsius, so it's dropping in temperature, so it's losing energy. So that's going to be the negative one, and this is going to be the positive one. So that's kind of just our talk up front. All right, so then Q of metal equals Q of water is how I set this up, where the metal gets a negative charge because it's losing energy. Then I substitute what in for this? Q equals MCAT, yeah, sorry, just making sure. So Q equals MCAT, and this is for the metal, and then this is positive Q MCAT for the water. So this is just generic setup. Just I want to walk you through the whole thing, and then from here you can kind of adjust how much you actually need to write. But what variable are you solving for? C of the metal, right? So this little guy right here, that's his blob now, solving for that. So how do I solve for that? Right, so I'm just dividing by negative m delta t over here. So dividing by m delta t, negative m, sorry, because that negative needs to go away as well. Dividing, and this is of metal, so I just put m on the outside to represent metal. And this is dividing, you're dividing by the same thing, so m delta t of the metal.
Why do we not divide by the same?
Because the C is what I'm isolating, because that's my question. So I'm keeping it, so like this negative cancels, the mass cancels, the delta T cancels, so C is now isolated by itself. C equals this big, huge thing. So MCAT over negative mass. Yeah.
Can you explain where the negative came from again?
Yeah. So whenever the metal is losing energy, the system is gaining it, right? So to represent that law of conservation of matter, we show that one of us is losing them and one of them is gaining it as a negative and a positive. And so that negative came here, which makes the negative of the negative Q, meaning heat loss from the metal, and it transfers with us. Okay, but the negatives in the end will cancel, so don't fret too much over it. Okay, so I'm going to plug everything in. C equals all this jazz. So I'm going to plug it in. So this is why the stat table is great, because you're like, oh, well, the mass of the water is 100 grams. Okay, what's the C of the water?
4.18.
4.18 joules per gram degree C. Okay. 2 degrees Celsius. All right, so that's the numerator. Let me see if I can scroll down just a tad. Okay, so 50 grams. Oh, don't forget the negative. You see there's a negative there? So it's a negative 50 grams times negative 59. Right. So do you see the negatives? The negative on the bottom that we carried, and the negative from the negative 59, they will cancel each other out to leave us with a positive overall value. All right, get those fingers to work.
Just 0.28 makes sense.
Hmm? Let me see if anybody else will give me a second calculation here. Anybody? Point 283, 0.283. Yep. Jeez. 0.283. Let's look that up here. All right. What are the units though? Did you cancel all the units, or you just knew that? Partially both? Okay. So this is the C of the metal, 0.283 joules per gram degree C. And then you're like, does that make sense? Yes, because metals have low specific heat capacities, and it's in joules per gram degree C. Let's verify that all the units canceled, except for those. So grams on top, yep, grams on bottom, great. Degree C on top, degree C on the bottom, great. So the only thing left are the units of joules per gram degree C. So that is why that exists there. Okay, so it's a little longer, but it's not that much harder because it's just the same scenario but together now. And so a picture for this one that you might want to draw on your foldable, this is calorimetry. How do we do all this nonsense? We put it in a styrofoam cup with water in it, and we drop some metal in there. His name is Metal, and he's real hot, so he releases the heat. These are like heat waves. And then how do I measure that heat difference? With a thermometer. That's a great drawing. There we go. That's basically what we're going to do in the lab. I know, you're so excited. Okay, so get a stretch break for a second. I have 2 more things I need to tell you. Okay, stretch break. Or not, I mean, whatever you want to do. But video is sexy. We can do yoga. Can you do my treat today? You're good. No one's saying.
Can we just finish Shavasana? Wait, Shavasana is
That's laying down.
Yeah.
Take just a minute, please.
For the lighting of what you okay, but when you're looking at like how it's at the time okay, so we were gonna go into the back really quickly. Oh, you're buying me food? Okay. But that was like where you were driving for it to be here, so we decided we were gonna do that. Yeah. No point against me. Well, we're going to do the class for next 1 hour. I was trying to make sure my guests didn't see when we did go on a date, and then I'm like, oh no. Will work better than I know.
Yeah, so my car is going 10 miles per hour.
I called him and said your car's like
The fully over. Then you see spend it.
and it's the burner or spray whatever it is, we'll just squeeze stuff out of it or
I was going to say, back in my
and then we will be I'm gonna monitor my car. And how am I holding myself like we're editing our like design form? How would you kind of flow? So
How would you Sorry. Okay, back with me.
it works. It's fine. It's a car that works.
All right. This is the third flap. This is information for Q equals moles times delta H. And I have to give you a couple values to write down under this one, so you'll utilize it in one of our problems. And if you still don't know what C is, here you go. That's not really relevant for part 3. It's just there. Just there. Thank you for bearing with me. It's almost Friday, and it's fourth period after a holiday. This is the most notes we'll take probably almost this whole unit. We got another day like this one. Okay, so Q equals moles times delta H. What do you notice is not there? What's not changing? No temperature change, right? So if you read a problem and you're like, oh, it says the temperature changes from 20 to 25. Would you use this formula?
No.
Lucas is like, heck yeah, I'd use it. No, you would not use it because there is no temperature change. So do not use this formula if there is temperature change. Only use it under phase change conditions. So phase change conditions means you'd have a little graph, like what? The stairs, right? So like this portion here is a phase change and this portion here is a phase change. So we've seen this now 3 times. So the 2 phase changes that we generally will see is melting and vaporization. So which of these represents melting? H fuzz or H vap? Fuzz. Okay, so this is our melting, and the vaporization, evaporation is our H vap one. For water, we actually have standard values for these. So delta H fusion is a value I'm going to have you write down so you always have access to it. It's also in your textbook. It's 6.01 kilojoules per mole. And delta H of vaporization is 40.6 kilojoules per mole. A lot bigger, right? And that's just because vaporization takes so much more energy to overcome those intermolecular forces. So these are 2 values I will give you. I do not expect you to memorize them, but you might accidentally. It's cool. All right, so in this case, basically, I might give you,
So this is solely for water?
yeah, this is only for water. Good point. And most of our examples are going to be about water, just because that's we know our C of water, we know our density of water, we know the molar mass of water, we know a lot about water. Huh? Water is awesome. I like it. Most days. Okay, so whenever you have an example like this, I will probably not give you moles. I will give you grams, because you can convert to moles. So don't forget that you can easily use grams to get your moles to use that equation. So let's do an example. I'm giving you one example of each type so that you don't have to do them at home and so that you have an example to look back at. Okay, here we go. Not sure so. Here we go. Oh, no, lies. Here we go. So, here's our first question under the last section. How many grams of water at blah, 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 blah. Okay. So, tell me what information I know. So, what's my question? So, grams of water. Okay. What else do I know? Okay, so that means it's boiling, right? At our atmosphere, at 1 atmosphere pressure. Nobody cares what that is, okay? That stuff is always given to you in the problem because it's not serving as a distractor. It's just like customary information you give whenever you're talking about phase change. Okay, because you can see that the water is being vaporized. Where you're like, no crap, it's at 100 degrees Celsius because that's when it vaporizes. Nobody cares, all right? So just note that these things in the middle, just cross them out because I don't want you to think it's a gas law. Okay? Cool? Okay. So how many grams of water could be vaporized Okay, so we know we're talking about vaporization by the addition of 180 kilojoules of heat. What is that variable? Say it again. Okay, remember, heat is different than temperature.
Delta.
No. It's Q. Heat is Q. Heat is Q. I'm going to tattoo that on you people, okay? Heat is Q. Q is 180 kilojoules. Okay, but there's this other value that you were trying to tell me, but you already know it. So if vaporization is happening, that means phase change of vaporization is happening. We know the energy of that vaporization. That's what you know already. You know delta HVAC. What is it? 40.6 kilojoules per mole. So this is a known. It's just not going to be given straight out in the column. It's just on your paper. Okay, so we know HVAC. We know Q. We want to know grams, but what probably should we find first before we convert to grams? Moles. So I'm just going to say like that's our secret question. Our real first question is what is moles? So if we want to find moles, we have HVAC, we have Q. What formula are we using? The one we just talked about right before this question. Yeah. There you go. Q is equal to moles times delta H. Huh? Impact. There's no delta T. Okay. So then how do I solve for moles? Divide by what? Delta H. So mole is equal to Q divided by delta H. So plug, plug, plug. Q is 180 kilojoules. Delta H is 40.6 kilojoules per mole. So what units cancel? Kilojoules. And you just get moles, which is what we're looking for, right?
Oh, this one's moving.
So what is that?
4.43.
4.43 moles. Okay, I'm running out of space a little bit. So that was our first question. But our secret question was what were the grams? So what's my last step? What is that molar mass? Right, 1 mole of water is about 18 grams per mole. Just simply adding up hydrogen plus oxygen. And 79 point what? 74. 79.74 grams of water. So, long story short, 180 kilojoules of heat will melt about 80 grams of water. Yeah. 180 kilojoules of heat will melt about 80 grams of water. Vaporize. Sorry. Vaporize. We're talking about vaporization. I have one more for you, but I'm gonna let you guys practice for a couple minutes first. So on the paper I gave you, I want you to circle the ones I want you to do right now, and if you don't finish, you'll finish later. Like AK for homework. So on the first set, from 1 through 4, you're gonna do number 2. Note there that you're gonna have to look up the specific heat capacity. What do I mean by that? No, but I'm looking for C, variable. Yeah, you will look up on your phone in a second. So you're going to look for C of iron. Because it's in your textbook, it's expected that you have access to that information. So you're going to look for the C of iron. All right, so that's number 2. What's up? Alex, what's up?
Talking about the lecture notes.
Yep. So I did number 1 for you, you're doing number 2. Calorimetry problems, you're going to do 2, 3, and 4. Phase change problems, you're going to do 2 and 3. And I'll do 4 and 5 for you. So please start on one of those now. I will note on number 2 in the calorimetry problems, do you see that calorie per gram degree C? Do you see that in there?
Yeah, what is that?
Okay, so calories, we all know what calories are. We eat them every day. Tasty points. Right? Tasty points. I like that. Okay, so I want you to know that for water, 1 calorie is equal to 4.18 joules. Is that familiar? Yes. So the specific heat of water, which is 4.18 joules per gram degree C, what do you think the specific heat of water is in terms of calories? 1 calorie per gram degree C. So this is the C for water. This is in terms of joules, this is in terms of calories, just because this is the equivalency between them. So you're going to want to use this one in number 2 on the calorimetry problem. We'll talk about what calories are. I think didn't we talk about like calories in bananas?
No.
Maybe this is my AP class. I can't remember. Okay, so I'll tell you about that in a second. Go ahead and start one of these right now so you can get my help as you need it. I'm gonna give you guys about 10 minutes to practice right now.
I just looked up. There's no one.
Alright, guys, if I'm giving you time to practice, use it or I'll keep going. Okay, please use this time. I'm giving you 10 minutes. You should probably at least get two or three now.
And then this is.
Yes. Oh, yeah.
So then I can.
Yeah, you're right.
So we're finding you.
So do you do 20 minutes?
Yeah, you do the final.
I definitely have one.
This is to this one. Yeah, so which
Yeah. There's Delta. So it'll be 20.
Are we looking for?
So which one have we got first?
Well, do we see that? You can see that it's going from 20 to 40, and so 40 is the top, 20 is the initial pressure, so the difference is okay, and then performance is here. I know it's what you guys will do, but we'll see, finally, because it's a difference, but it's expected to do acid to it, which is